We are now ready to learn about the key algorithmic technique called dynamic programming. And to learn about the dynamic programming, we will look at a very simple change problem. You walk to a supermarket, you pay for Campo and Pevsner book, and you have 40 cents in change. And now cashier is making a decision how to give you this change. The cashier can give you a quarter, a dime, an extra 5 cents, and it will be 3 coins. But cashier also has a choice of giving you 40 pennies. The change problem is to find the minimum number of coins to change a given amount of money. And the first thing that comes to mind is actually the approach that cashiers all over the world use. They simply look at the amount of money they have to change, and they find the maximum denomination, maximum amount, maximum coin that doesn't exceed the money. They give you this coin, subtract this coin from the amount of money, and iterate. Do you think this approach would produce an optimal solution? In fact, it will produce an optimal solution in the United States, but not in Tanzania. Tanzania has beautiful coin shown here, and they actually, in addition to quarters, they have a 20 cents coin. So while greedy algorithm in Tanzania will result in 3 coins as a change, because it starts from 25, the largest coin, smaller than 40, then adds 10, that's fine. The right thing to change money in Tanzania is simply to give you 2 20 cents coin. So what algorithm should we design to change money in Tanzania optimally? Let's design a recursive change algorithm. And let's imagine that we are in a strange country where there are only 3 coins, 6 cents, 5 cents, and 1 cent. How would we change 9 cents using this coin? Well, to change 9 cents, to find optimal amount of money, or optimal minimum number of coins to change 9 cents, we can find minimum number of coins to change 8 cents and to add 1 penny, or minimum number of coins to change 4 cents and to add 5 cents coin, 1 more coin, or to find minimum number of coins to change 3 cents and add 1 more coin, right? And therefore, minimum number of coins for 9 cents is minimum of minimum number of coins for 8, 4, or 3 cents plus 1. Make sense? Okay. But to find minimum number of coins for 3, 4, and 8 cents, we once again need to find minimum number of coins for other values of money, and we will be doing this recursively. So the general formula for whatever number of coins we may have for denomination will be minimum number of coins for the amount of money equal minimum of the following D expressions, where D is the number of coins in the currency. It is minimum number of money for money minus coin 1, minimum number of money, or minimum number of coins for money minus coin 2, and finally minimum number of coins for money minus coin D, plus 1 for all these values. And there is a simple recursive change algorithm that implements this approach. So every time we need to change the amount of coins equal money, we have D recursive calls and compute the minimum number of change for money minus coin I. Do you think it is a good algorithm? This algorithm is definitely correct, but it will take quite enormous time to solve the problem. Let's see how it works. Let's start from 76 cents and see how algorithm works. To compute the change for 76 cents, we need to compute first the change for 70 cents, 71 cents, and 72 cents, right? Yes, 75 cents. And we continue this way recursively, and we see that to compute 76 cents, we actually need to compute optimal amount of change for 69 cents twice. But if we go further, we see that we actually need to compute it more than twice. Now we see that we need to compute it 5 times. In reality, we actually need to compute optimal coin combination for 69 cents 6 times. Okay? So, but how many times we need to compute optimal combination for 30 cents? It turns out that we need to compute it trillions of times, which means that our algorithm is correct, but it will never end because it takes so much time. We need to come up with a different approach. Instead of changing money greedily, let's try something different. Wouldn't it be wonderful to compute all the values, minimum number of coins for money minus coin I, that all values that we need to compute minimum number of coins for the amount of money? If we pre-computed all these values, then computed minimum number of coins for given amount of money would be a simple exercise and very fast exercise, right? And to implement it, the only thing that we need, instead of the time-consuming calls to recursive change for money minus coin I, we simply look up the values of minimum number of money coins for money minus coin. So how our algorithm change? We'll, instead of moving from larger value to smaller values to fill this table, we will now move from smaller values to larger values. For example, what is the minimum number of coins to change 0 cents? Of course, it is 0. What is the minimum number of coins to change 1 cent? Of course, it is 1. 2, it is 2. 3, it is 3. And 4, it is 4. And now we come to changing 5 coins. And they can be changed in 2 different ways. They can be changed either by taking minimum number of coins to change 0 and adding 1 coin, or minimum number of coins to change 4 and adding 1 coin. Which of these numbers is smaller? This is a simple check, and we choose to change 5 coin by adding 5 cents coin to existing combination. Now we are facing with the problem of changing 6 cents. In this case, there are 3 choices. We can either use optimal change for 5 cents, or 1 cent, or 0 cents. And depending on which of them is the smallest, we'll decide how to change 6 cents. So in this case, it turned out that the best strategy is simply to add 6 cents coin to the combination. We continue further and further until we arrive to changing 9 coins. Of course, it is a much faster algorithm, and we can implement it differently without any recursive coins. Simply at every stage, to compute amount of money, we need to run D, look at D previously computed values, where D is the number of denominations. That's all. That's the idea developed by Richard Bellman and called dynamic programming, which is arguably the most popular algorithmic technique today. Amazingly, 60 years ago, when Richard Bellman was developing this technique, it was absolutely unclear that this technique has any practical applications. In fact, Richard Bellman was working on a project for Air Force. And it turned out, some students sometimes ask you, where is programming in dynamic programming? It turned out there is no programming in dynamic programming, because at that time his approach seemed completely impractical. And he worked for Air Force, so he wanted to hide that he is really doing mathematics from the Secretary of Defense. He was a prominent mathematician by this time. This is a quote from Richard Bellman. What name could I choose? I was interested in planning, but planning is not a good word for various reasons. I decided, therefore, to use the word programming, and I wanted to get across the idea that this was dynamic. It was something not even a congressman could object to, so I use it as an umbrella for my activities. So amazingly enough, the most popular algorithmic technique today was invented as an umbrella for the for mathematical activity while working on the Air Force project.